All right, section 27.5, which is the last section that we covered last time that we met, was the section on derivatives of logarithmic functions. All right. So we introduced a new rule, and then we also looked at logarithmic functions when we need a chain rule, product rule, or quotient rule. So we're going to just continue on here. Just as a reminder, the derivative with respect to x of a log with a random base number a of x is equal to 1 over x times natural log of a. And then when we're specifically looking at the natural log, so the derivative of a function natural log of x with respect to x simply equal to 1 over x, right? So those two are added to your list of basic derivatives. All right, so we will also then look at the derivatives of exponential functions, all right? And so specifically, the first one we will look at, the derivative with respect to x of a raised to a power x is equal to a raised to a power x times the natural log of a. The derivative with respect to x of e raised to the power x is e to the x. All right, so I want to back up here and just quickly address sort of a common careless error. That's not it. Here it is. All right, so I want you guys to kind of just quickly help me put some examples of functions into their families of functions. All right, so the first one I have for you, f of x is equal to x squared. Can you tell me how to categorize this function? It is parabolic. How about that guy? Could you come up with one sort of family of functions that we could put all of those guys into? This is a power function, right? All right, so write them down again. F of x is equal to x squared. This is a power function. All right, and so when we take derivative of a power function, we use the power rule. All right, the power rule said when you take derivative of a power function, so for instance, a power function we said was a coefficient times x to the power n. So when we found a derivative, it was equal to n times c times x to the power n minus 1. Remember the power rule of derivation? We use the power rule when we have a power function. What type of a function is this? How do we categorize this guy? That's an exponential. Very good. This is an exponential function. Do you think that it is appropriate to use the power rule that is meant for power functions to find the derivative of an exponential function? It is not, right? So we don't use the power rule when we're dealing with exponential functions. Exponential functions will have their very own rule. And that rule, like we just saw, was this. So if you had f of x equals 2 to the power x, then the derivative f prime of x is 2 to the power x times natural log of 2. Okay? So don't confuse power functions with exponential functions. All right, so let's see if we can use these rules of finding derivatives of exponentials to give the derivative of y equals e raised to the power negative 5x times cosine of 3x. I'm going to need to use both the product rule and the chain rule for this example. So y prime is equal to, let's start by finding derivative just of the first. Let's separate these guys. So the first and the second. Derivative of e raised to the power negative 5x. So by the chain rule, derivative of the outside. Derivative of e raised to some power is e raised to that power times derivative of the inside. The derivative of negative 5x is equal to negative 5. So all of this stuff here together, this constitutes derivative of the first times the second plus the first. The first is just e to the negative 5x times derivative of the second. All right, so help me out here. Derivative of cosine of 3x. This is going to, again, require the chain rule. Derivative of the outside, derivative of cosine is equal to negative sine. Leave the inside alone, so leave the 3x alone, times derivative of the inside, derivative of 3x equal to 3. All right, questions? Okay, that's good. All right, this example was like really advanced for a first example. Let me insert another example for you guys here. Please find for me the derivative of f of x is equal to e raised to the power x squared plus 1. What will the derivative be equal to? All right, so this is a composite function. The outside function is e raised to some power. The inside function is x squared plus 1, right? So derivative of the outside. What is the derivative of e to the x? It's just e to the x. Derivative of e to some power is just e to that power. So derivative of the outside is just e raised to the power x squared plus 1. Times derivative of the inside. What is the derivative of x squared plus 1? 2x. Okay? How about, let me ask you this one first. All right, g of x is equal to 4 raised to the power x. The derivative, g prime of x, is equal to 4 to the power x times natural log of 4, right? Now let's complicate this just a little bit. What if I give you a function h of x is equal to 4 raised to the power sine of x? Is this still an exponential function? What do you think? By the way that we categorize these, is this still an exponential function? It is, because my variable x shows up in the exponent and in the exponent only. So yes, this qualifies as an exponential function. However, it is composite. What would you, the outside function here is what? 4 raised to some power, right? So the outside function is 4 raised to the power x, or 4 raised to some power. The inside function is sine of x. So when we take the derivative here, h prime of x, again, just take derivative of the outside. What is the derivative of 4 to the power x? 4 to the x times natural log of 4. All right, but now just instead of x, we have a function plugged in there. So the derivative of the outside would be 4 to the power, just leave the inside alone. So 4 to the power times natural log of 4 times, now we get to take derivative of the inside. What is the derivative of sine of x? It is cosine of x. Right. You guys okay so far? All right, let's look at more of these examples that are given here. Number 2, f of x is equal to 3x raised to the power 6 times e raised to the power 2x. So here again, we're going to have to use both the product rule and the quotient rule to find this derivative. All right, so f prime of x is equal to, So again, in my product, I'm going to just make sure I clearly indicate this is the first, this is the second. So the product rule says this will be derivative of the first, so that is the derivative of 3x to the power 6. That's equal to 18x to the power 5, derivative of the first, times the second, e to the 2x, plus the first, 3x to the power 6, times derivative of the second. All right, what is derivative of e to the 2x? By the chain rule, derivative of the outside would be e to the 2x times derivative of the inside, which is equal to 2. All right. Any of these examples you want to look at again? Are you guys okay with these? Because we're going to move on and we're going to start using these in bigger problems. All right, we're good? Okay. All right, so the next section we're going to introduce to you is something called L'Hopital's rule. So if you guys remember, right at the beginning of the semester, we spent a great deal of time learning how to take limits of different functions. All right, so if we quickly go back and we recap our approach to limits, if I randomly gave you a limit, what would you do first to that limit? You're going to go ahead and just plug that value in and see what happens. Either you can plug the value in and you do not violate the domain of that function, and you can simply just evaluate and give me a value back, right? But oftentimes when you plug that limit into the function, you do violate the domain, so you can't just plug it in. So we had cases where we either had 0 over 0 or infinity minus infinity. We had different, what we called indeterminate cases, in which case we did what? Kind of develop the expression a little bit, right? So either we factored, so if we had a rational expression, we would either factor or expand, cancel out some terms or combine some terms. So in a sense, we would just develop the expression, and then each time we clean it up, we try to plug that limit in again to see if it worked, right? So the second method was simplify the expression and then evaluate again, right? So now we're going to introduce another way of evaluating limits that's even better, but it relies on us having some knowledge of differentiation, which is why we couldn't introduce it back at the beginning of the chapter, right? So L'Hopital's rule relies on differentiation. And the rule says the following. All right, suppose that we have two functions, f of x and g of x. Both of these two functions are differentiable, and that g prime of x is not equal to 0. All right. So what we're going to try and do is we're going to take the limit as x approaches a of f of x over g of x. So it's important to note here that our limit is in the form of a fraction, right? It's a rational expression. We're going to plug that limit in, and if we see 0 over 0, we're going to assume that we are in the special case, right? So 0 over 0 is the first indeterminate case. The other indeterminate case we're going to look out for, the limit as x approaches a of f of x over g of x is equal to either plus or minus infinity over infinity. Either one of these two forms are called my indeterminate forms. If I am in this form, we may go ahead and apply L'Hopital's rule, which says that the limit as x approaches a of f of x over g of x will be equal to the limit as x approaches a of f prime of x divided by g prime of x. All right. All right, so let's check quickly. Let's apply. All right. Example number 1. We have the limit as x approaches -2 of x squared minus 4 divided by x plus 2. All right, so back in the first chapters that we covered, what we would have done here is we would have simply plugged this in. So let me show. Wrong one. What I would have done is I would have plugged it in. If you plug -2 in, this would have been equal to negative 2 squared minus 4 divided by negative 2 plus 2, it would have been equal to 0 over 0, right? So instead what we're going to do, or if this was the case, if it was 0 over 0, I would say, all right, let's take this limit and let's go ahead and factor. So x squared minus 4 can factor into x minus 2 times x plus 2 divided by x plus 2, right? And we will then notice that, all right, so we have these two factors that can cancel out. So we have the limit as x approaches negative 2 of x minus 2 that I can now just evaluate. If I plug negative 2 in here, this will be equal to negative 2 minus 2, which is equal to negative 4. Right, this is the old method of doing it, which is still just fine. You can absolutely use that. However, we notice that since we have here the case that if I plug this limit in, I get 0 over 0. 0 over 0 now becomes a permission slip for me to use L'Hopital's rule. So that means that this limit is going to be equal to the limit as x approaches negative 2 of the derivative of the top. So what is the derivative of x squared minus 4? Equal to 2x, right? Divided by the derivative of x plus 2, which is equal to 1. And now we can take the limit again. So again, plug in negative 2. If we plug negative 2 in there, this will be equal to 2 times negative 2, which is equal to negative 4. So different method, but again, here you see that I get the same limit. All right, questions so far? All right, let's look at some more examples. Number 2, I have the limit as x approaches 0 of 1 minus e raised to the power a times x divided by x raised to the power 7. All right, so let's quickly address the elephant in the room. I have over here 1 minus e raised to the power a times x. There's two variables in this expression, right? Are they both variables? The limit is being taken with respect to x. So x is the only letter that I'm going to treat like a variable. Everything else will be treated as if it is a constant. So this number a over here that you see, you will treat that a as if you would treat any other constant. So if you want to consider that a to be a 9 or 11 or, give it some numerical value, all right? We treat it as if it is a constant. All right, so let's see. If I plug 0 in here, I will have 1 minus e raised to the power a times 0. That is e to the power 0, and e to the power 0 is equal to 1. 1 minus 1 is equal to 0. In the denominator, if I plug 0 in for x, I get 0. And so at this point, when I know that I am allowed to use L'Hopital's rule, seeing that outcome of 0 over 0 is good news. It means that's permission for me to go ahead and apply L'Hopital's rule. All right, so we get to use L'Hopital's. I'm going to take the derivative of the top and the derivative of the bottom. So we will have an equivalent limit. The limit as x approaches 0. Let's see, 1 minus e raised to the power a times x. The derivative of 1 is 0. The negative is just a coefficient, so hold it over. All right, derivative of e to some power. What is the derivative of e raised to a power? It is e to that power, leave the power alone, times, because this is composite, now we can take derivative of the inside. What is the derivative of a times x? A. So times a, very good. All over, what is the derivative of x to the power 7? 7x to the power 6. And now we can plug the limit in again. So really what we have right now is just a brand new limit problem. So plug it in again. If I plug 0 in, e raised to the power 0 is equal to 1. So this becomes 1, right? Let's go ahead and indicate that. This becomes 1. And if I plug 0 in here, the denominator becomes 0. So what I have is negative a divided by 0. All right, what do we say? What do we do with a limit when a limit is equal to a number over 0? It does not exist. Very good. So anytime a limit is equal to a number over 0, it means that either the limit from the left or the limit from the right approaches either positive or negative infinity. It could be that they both approach, the limit from the left and the limit from the right both approach infinity, in which case, in general, the limit will approach infinity, but we do say that it does not approach a finite number. So we can say that this limit does not exist, D and E. All right, problem number 3, we have the limit as x approaches 0 of sine of 10 times x divided by sine of b times x. All right, let's plug in 0. All right, so if you plug in 0, sine evaluated at 0 is equal to? What is the value of sine evaluated at 0? It is equal to 0. Sine evaluated at 0 is equal to 0. All right, so we see 0 over 0, which means I get to use L'Hopital's rule. All right, so the original limit then is equivalent to the limit as x approaches 0. All right, so let's take the derivative in the numerator. The derivative of sine evaluated at 10 times x. This is a composite function. Outside function is sine, and the derivative of sine is equal to cosine. So that'll be cosine, leave the inside alone, 10x, times derivative of the inside. What is the derivative of 10 times x? Derivative of 10x, 10. All right, in the bottom, same thing. Derivative of the outside. Derivative of sine is equal to cosine, leave the inside alone, b times x, times the derivative of the inside. Derivative of b times x is equal to b. All right, and now we attempt to take the limit again. So let's plug this in. If I plug 0 in for x, 10 times 0 is equal to 0. What is the value of cosine at 0? Cosine of 0 is equal to 1. Very good, thank you. Again, in the bottom, cosine evaluated at 0 is equal to 1. So all that's left here is 10 divided by b. All right, problem number 4. We have the limit as x approaches infinity of the natural log of x divided by x squared. We have limit as x approaches infinity of the natural log of x divided by x squared. All right, so you guys remember what the graph of natural log of x looks like, right? What is the limit as x approaches infinity of the natural log of x? Maybe in your best interest to quickly go ahead and grab that set of notes, right? Let's see. This was on page 118. All right, so here's the standard graph of a natural log. So as your x values start moving to the right, where are your y values moving? Up to the top, right? So as x goes to infinity, y goes to infinity also. All right, so the limit as x approaches infinity of the natural log of x is equal to infinity divided by, again, if I plug infinity in for x in the bottom, infinity squared is equal to infinity. All right, so this infinity divided by infinity is one of the two indeterminate forms. So we know that we can then use L'Hopital's rule. That's not good either. All right, so let's go ahead. Take the derivative of the top and the derivative of the bottom. So I have the limit as n goes to infinity. I'm sorry, not nx. The limit as x goes to infinity. All right, what is the derivative of the natural log of x, please? 1 over x. Divided by the derivative of x squared is equal to 2x. All right, so before I try to take this limit again, what I'm going to need to do is clean up my algebra. I'm going to go ahead and just simplify this expression. 1 over x divided by 2x, this is equal to the limit as x approaches infinity, essentially of 1 over x times 1 over 2x. And so we can combine this and state that this is the limit as x approaches infinity of 1 over 2x squared. All right, so we can plug infinity in. If I plug infinity in for x, infinity squared is equal to infinity. So we get 1 over infinity. And what is the value of 1 over infinity? If your denominator gets really, really, really big, your overall value gets really, really small. So this value goes to 0. All right, questions? No questions? All right. How about problem number 5? We have the limit as x approaches 1 of the natural log of x divided by x minus 1. All right, let's plug this limit in. What is the value of, I'm going to plug 1 in for x in the numerator. What is the value of natural log of 1? The natural log of 1 has what value? It is equal to 0. Thank you. Divided by, plug 1 in the denominator. 1 minus 1 is 0. All right, so there you have it. We have that 0 over 0 again. So we have 0 over 0. So we can use L'Hopital's rule. So I'm going to take this limit. I'm going to set it equal to the limit as x approaches 1. All right, derivative of the top. The derivative of the natural log of x is equal to 1 over x. And the derivative of the denominator, derivative of x minus 1, is equal to 1. Now this expression will just clean up to be equal to the limit as x approaches 1 of 1 over x. And you can simply plug in. If we plug in 1 for x, we see that this limit is equal to exactly 1. It would not be negative 1, no. Why would it be negative 1? Why? What's your reasoning? Because of this negative? So when we took the derivative, what happened was derivative of x is equal to 1. Derivative of negative x is equal to 0. No, that's okay. All right, let's see, number 6, I have the limit as x approaches 0 of sine of x divided by 1 minus cosine of x. All right, so by simply just plugging in this limit, I get sine of 0. Sine of 0 is equal to 0. Cosine of 0 is equal to 1, so 1 minus 1 also equal to 0. So I have my 0 over 0, my indeterminate form, which tells me that I need to go ahead and apply L'Hopital's rule. All right, so the original limit will be equivalent to the limit, sorry, this is an x. The limit as x approaches 0, I'm going to take the derivative of the numerator. Derivative of sine is equal to cosine over the derivative of the denominator. Derivative of 1 minus cosine of x is equal to positive sine of x. So there's more than one way that you can now approach this limit. You can either express, we know that cosine of x divided by sine over x is equal to cotangent, right? So you can either express it as cotangent and take the limit again, or you can go ahead and just take the limit at, or you can try to take the limit at this point in time. All right, if we take the limit right here, can I plug 0 in for x right here? Cosine evaluated at 0 is equal to 1. So what I will get here is 1 over, if I plug 0 in for x in the bottom, sine evaluated at 0 is equal to 0. All right, so what do we choose when we see that a limit is equal to a number over 0? Yeah, so anytime we see a number over 0, we say that this limit does not exist. So we started with a negative cosine. Yes, the derivative of cosine is negative sine times the negative that was already outside of it became positive sine of x. Okay. All right, let's see. Problem number 7. I have the limit as x approaches 0 of a raised to the power x minus 5 raised to the power x divided by 9 raised to the power x. Here again, a just represents a random constant, right? A here could have been 3 or 9 or 11 or any other number. So just treat it as if you would any other constant. All right, so if I plug in this limit, if I plug 0 in for x, a raised to the power 0 is equal to 1. 5 raised to the power 0 is equal to 1. 1 minus 1 is equal to 0. Divided by, if I plug 0 into the denominator, 9 times 0 is equal to 0. All right, so the 0 over 0 tells me that we are ready to use L'Hopital's rule. All right. So I will take the limit as x approaches 0 of, here we go. What is the derivative of a raised to the power x? It's not. So the mistake that you're making is that you are using the power rule of differentiation to take a derivative of an exponential function. So what was the rule for exponential functions? Derivative of a to the power x? A to the power x times natural log of a. Minus the derivative of 5 raised to the power x is 5 to the power x times the natural log of 5. All right, all over the derivative of 9x is equal to 9. And now we can go ahead and plug the limit in again. Here we go. If I plug 0 in for x, a to the power 0 is, that's just equal to 1. 5 to the power 0 is 1. So we're simply left with the natural log of a minus the natural log of 5 divided by 9. Which right now I can't simplify any more than this, but had the value of a been known to me, this is a value that I could plug in my calculator and I can get a constant value for my answer. We will leave our answer right here, though. All right, problem number 8. We have the limit as x approaches 0 of 1 plus x minus e raised to the power x divided by 3x squared. All right, again, let's see what happens when we plug in 0 for x. I will have 1 plus 0 minus e raised to the power 0 is equal to 1. So I have 1 plus 0 minus 1. That's equal to 0. If I plug 0 in for x in the denominator, 3 times 0 squared is 0. All right, so we see our 0 over 0. That is our permission slip to use L'Hopital's rule. So this limit will be equal to the limit as x approaches 0. And let's take the derivative of the numerator. Derivative of 1 is equal to 0. Derivative of x is equal to 1. And derivative of e raised to the power x is e to the power x. All right? In the denominator, the derivative of 3x squared is equal to 6x. Brand new problem. Let's plug in this limit again. All right, if I plug 0 in for x, I will get, let's see, e to the power 0 is equal to 1. 1 minus 1 is equal to 0. If I plug 0 in for x in the denominator, I get 0 again. All right, so is it okay to use L'Hopital's rule more than once per problem? Absolutely, that's fine. So we're going to do another iteration of L'Hopital's. All right, so I have the limit as x approaches 0. Let's take the derivative of the numerator. Derivative of 1 is equal to 0. Negative is a coefficient, put them down, and the derivative of e to the x is e to the x. In the denominator, the derivative of 6x is equal to 6. All right, and one more time, go ahead and plug in 0 for x. E raised to the power 0 is equal to 1. And so we can see that this limit is equal to negative 1 over 6. All right. All right, let's do this. Muddiest point. Which one of the examples that we have just covered in the last 2 pages is the one that you understand least, or the one that you want to see again, or the one that you have a question about? Mm-hmm. If I have a composite function, yes, then I use the chain rule and I take derivative of the outside times derivative of the inside. I did not have a composite function here, though. Okay. Yes?
Did you get the wrong answer if you used this rule multiple times when you didn't need to? You did it twice on one that you only need to do it once on. Would it give you a wrong answer?
I would say that yes, it would probably be wrong because if your expression has to first, your limit first has to take on this form of 0 over 0 or infinity over infinity before you're able to apply L'Hopital's rule. You can't use L'Hopital's rule if you don't first see 0 over 0 or infinity over infinity. So if you're using it when it's not appropriate to use, it probably indicates that you evaluated it incorrectly to begin with. Okay. All right, you guys tell me, which one of these examples do you want me to look at a little bit closer? Am I to assume that everybody in here understands every one of these examples completely? Number 7? Yeah, all right, so for number 7, let me give you some prerequisite practice here. We said that if we have an exponential function, f of x is equal to a raised to the power x, what is the derivative equal to? What's the derivative of a raised to the power x? So flip back to the page where we introduced exponential differentiation. It was on page, right there, page 120, right? What is the derivative of a raised to the power x? It is a to the power x times natural log of a, right? You can replace a with anything here. A here represents some constant, all right? And in this case, a represents a constant. So the derivative of a to the power x is a to the power x times natural log of a. All right, so then in a similar fashion, what is the derivative if I give you a function g of x is equal to 5 raised to the power x? G prime of x is equal to 5 to the power x times the natural log of 5. Okay, you with me there? All right, so these derivatives are very simply just derivatives by definition. So this is a definition that you just have to know. All right, so back to the problem then. The limit as x approaches 0 of a to the power x minus 5 to the power x divided by 9x. So if I ask you to go ahead and take this limit, if you plug 0 in there, a to the power 0 is equal to? Anything to the power 0 is equal to 1. So you have a to the power 0 minus 5 to the power 0. You have 1 minus 1. 1 minus 1 is equal to 0. Plug 0 in the denominator also. 9 times 0 is 0. All right, so you see the 0 over 0 form. This is the indeterminate form. This is good because this gives me permission to now use L'Hopital's rule. So now it says I can go ahead and apply this rule. All right, so that means what we get to do is we get to equate this limit to a limit of the derivative of the numerator divided by the derivative of the denominator. So let's take the derivative of the numerator. Derivative of a times x, you just told me was a, not a times x, a raised to the power x is a to the power x times natural log of a minus the derivative of 5 to the power x is 5 to the power x times natural log of 5. All over the derivative of 9 times x is 9. Okay, and now we evaluate again. So now we just try to plug things in again. So again, if you plug 0 in for x, a raised to the power 0 is, this term is just equal to 1. Same thing here, plug 0 in for x, 5 to the power x, this guy is equal to 1. Right, so if those are equal to 1, you have the natural log of a minus the natural log of 5 divided by 9. So if I gave you a value for a, if I say a is equal to 3, this is equal to a constant value that you can find on your calculator. But until I give you that value a, you're just going to leave it right there in that form. Okay? Any other ones?
Can we go back to number 6 below as the sin x?
Sure. All right, so are you with me on the first? You see that if I plug in 0, do you get the 0 over 0? Is that good, or do we need to?
Yeah, I'm good all the way up to that point when you said something about cotangent x.
Okay, so what I'm saying is, okay, so one way of solving this is the way that, so I left this as the limit as x approaches 0 of cosine of x divided by sine of x. And if you plug 0, if you plug this limit in for each one of these, cosine evaluated at 0 is equal to 1. Sine evaluated at 0 is equal to 0, and we know 1 over 0 indicates that the limit does not exist, right? So what you could have done here is you could have said, all right, if we had the limit as x approaches 0 is equal to cosine of x divided by sine of x. This is just an alternative way that you could have solved this. What is, so use trig to tell me what is cosine divided by sine? Cotangent. So this is equal to the limit as x approaches 0 of cotangent of x. So now you would need to go back to that section where we introduced the trig functions, and I gave you guys a unit circle, or you could look at that table of values that I gave you. What is cotangent evaluated at 0? It is undefined. It is undefined. It is undefined. So you could look at it from either perspective. Either this or this gives you the same outcome. Right? Does not exist or undefined really means the same thing in this context. Okay. Yeah. Any other ones before I move on? Yeah, good. All right, so we would like to take a look at something called, it's an indeterminate form that we're going to call the form infinity times 0. So all of the forms that we just saw were either 0 over 0 or infinity over infinity, which is great because that is exactly the form that it needs to be in for me to be allowed to use L'Hopital's rule. But problems don't always present themselves in that form. Sometimes it takes just a little bit of work from me to adjust the function so that it would be in the form 0 over 0 or infinity divided by infinity. And so it's really easy to tell because I'm being given a function here that is not a rational expression or a fractional expression, right? Instead, I have x to the power 4 times the natural log of x. So let's quickly look and see what happens. If we are faced with a limit as x approaches a of f of x times g of x, and this limit, when you plug it in, equals either 0 times infinity or infinity times 0, then that means that you could possibly get the indeterminate form that you're looking for out of this, but it means that either one of these two functions will have to be moved to the denominator. Well, you can't just move it. You have to make sure that your function remains equivalent to the original expression. So when I say that you're going to move g of x to the denominator, it will become 1 over g of x when you move it down here. Or you could move f of x, and it will become g of x divided by 1 over f of x. Right? And so now you have that fractional expression that may give you either 0 over 0 or infinity over infinity. Right? So an example here, number 9. I have the limit as x approaches 0 from the right of x raised to the power 4 times the natural log of x. So let's quickly plug in and see what happens. Before I plug in, though, let's quickly revisit logarithms. What is the limit as x approaches 0 from the right-hand side of the graph of natural log of x? So again, this may be worth you just, again, pulling out that graph that I gave you guys. So I know that this graph right here is given as log base 2 of x, but it is a parent graph, so the graph of log base e of x or natural log of x will have a similar shape, size, and position. All right, so if you're walking on this function, if you're walking on this graph, if you're approaching 0 from the right-hand side, what values are your y values approaching? Negative infinity, all right? So here's something that I would say pretty much you need to go ahead and memorize. The limit as x approaches 0 from the right-hand side of log base a of x or the natural log of x is equal to negative infinity. This guy pops up quite frequently. All right, and so we see it here. The limit as x approaches 0 from the right-hand side. All right, so if I plug 0 in here, plug in 0 for x, that's equal to 0 times. If I take the limit as x approaches 0 from the right of natural log of x, you guys just told me that that's equal to negative infinity. And so here we see it. Here's the form of 0 times infinity. It's okay if it's negative infinity. Negatives factor out. But you see, we see this 0 times infinity form. This is what's popping up here. So that tells me either one of these two components needs to be moved into the denominator. All right, and the rule that I will give you guys is typically, if you have an expression that already has a negative exponent, move that guy, if it already has a negative exponent. If you don't have anything raised to a negative exponent, move the algebraic component. So in this case, x to the power 4 is the algebraic component. ln of x is the logarithmic component. Move the algebraic. Right? So when you move it to the bottom, it either becomes, you can write it as the limit as x approaches 0 of the natural log of x divided by, you can either write it as x to the power negative 4, or, doesn't matter, you can write it as natural log of x divided by 1 over x to the power 4. So my expression is equivalent, but it now takes that fractional structure. All right, so if I now plug in this limit, the natural log is still going to be approaching negative infinity. Nothing changed there. But if I plug 0 in for x over here, what is 1 over 0? 1 over a really, really, really small number will become a really big number. Is that right? All right. So the limit as x approaches 0 of 1 over x to the power 4 equal to infinity. All right, and so here I see this is the form that I was after. I was hoping for infinity over infinity, and now we have it. So once we see infinity over infinity, that means we may proceed with L'Hopital's. So I'm going to use L'Hopital's rule. So this will be the limit as x approaches 0 from the right-hand side. All right, derivative of the top. The derivative of natural log of x is equal to 1 over x divided by the derivative of 1 over x to the power 4. You know what? Let's do this. Let's quickly find what this is. The derivative with respect to x of 1 over x to the power 4. This is the derivative of x to the power negative 4. This is equal to derivative of x to the power negative 4 is negative 4x to the power negative 5. I don't like leaving things with negative exponents though, so I'm going to write this as negative 4 divided by x to the power positive 5. All right, so what's the derivative of 1 over x to the power 4? It is negative 4 divided by x to the power 5. All right, how do I solve an expression that includes a complex fraction? I want to definitely clean up my algebra before I do any more calculus. I'm not even going to try to take this limit before I've cleaned up this expression. How do we solve a complex fraction? We multiply by the reciprocal of this denominator, right? So this fraction will come to the top. I'm going to multiply him, provided that I flip the fraction. So this is going to be equal to the limit as x approaches 0 of 1 over x times x to the power 5 divided by negative 4. All right, what do we have if we clean this up? X to the power 5 divided by x. One of these x's will cancel out, right? And this will be equal to x to the power 4 divided by negative 4. And at this point, we can actually take the limit again. So plug the limit in. If I plug in 0 for x, this is equal to 0 to the power 4 over negative 4, which is equal to 0. All right, questions? All right, so guide me to which step you're at. Over here?
No, at the bottom, right at the end.
Here? So we had x to the power 5 divided by x to the power 1. Simplifies and just becomes x to the power 4. Yes?
What route would you say would be better, the x to the negative fourth or the 1 over x to the
It really doesn't matter. I mean, it's completely equivalent. It really doesn't matter. For me, it's easier to work with an expression that does not have negative exponents, because as long as your expression contains negative exponents, you really can't cancel out or do arithmetic. So either way, I mean, it's really the same, because after you take the derivative, just make sure that you clean up your derivative when you plug it back in. Okay. All right. Okay. I have one more example here for you guys. Problem number 10 is the limit as x approaches infinity of x to the power 5 times e raised to the power negative x to the 4th. So in this case, I do have an algebraic term and an exponential term. I said always move the algebraic term, except if you have a negative exponent. If you have a negative exponent, that's always the thing that you want to move. All right. So I'm going to, first of all, if you plug infinity in here, infinity raised to the power 5 is infinity. If I plug infinity in here for x, e raised to the power negative infinity becomes 1 over e to the power infinity, which is equal to 0. So we have that infinity times 0 form. So I know something is going to have to move. I'm going to write this as the limit as x approaches infinity of, I'm going to leave x to the power 5 in the numerator. I'm going to move this term to the denominator, e raised to the power x to the 4th. All right, so if I now plug in infinity, you guys see that we get infinity over infinity, which means this is a very nice L'Hopital's rule problem. All right, so let's see. We're going to take derivatives. I'm going to take derivative of the top. Derivative of x to the power 5 is 5x to the power 4 divided by, all right, and now you guys have to be prepared to use chain rule. The derivative of e raised to the power x to the 4th. All right, so first of all, what is the derivative of e to some power? The derivative of e to the x is e to the x. Derivative of e to a power is e to that power. Times derivative of the inside. Derivative of x to the power 4 is 4x cubed. And again, clean up your algebra before you proceed with your calculus. This will be equal to the limit as x approaches infinity. I will have 5 divided by 4. I'm just going to regroup, so I'm going to put all my coefficients out front. What is x to the power 4 divided by x to the power 3? After I cancel out x to the power 4 over x to the power 3, we just have an x left up here. And down here we have e to the x to the 4th. All right, so we'll do this one more time. I'm going to plug in this limit. If I plug in infinity, you guys see that again, we have infinity up here divided by e raised to the power infinity is infinity. So I get infinity over infinity again. So we can do one more step of L'Hopital's. So we will have the limit as x approaches infinity. All right, the derivative of 5x is equal to just 5. 4 is a coefficient, so just leave them alone. Coefficients hold over. And again, the derivative of e raised to the power x to the 4th is equal to, derivative of the outside is e raised to the x to the 4th times derivative of the inside. Derivative of x to the power 4 is 4x cubed. And again, I usually advocate cleaning up your algebra before you do your calculus, but at this point in time, what happens if we plug infinity in for x? We have 5 divided by infinity times infinity. We end up with 5 divided by infinity, which is equal to 0. Yes? I'm sorry, what was that?
You moved the 4 down from that. Why is that?
This 4 is not a constant, it's a coefficient. So the 4 is being multiplied by the function. So when we take derivative, coefficients just hold over. Derivative of 4x is just equal to 4. So coefficients always hold over. Does that answer your question? Okay. Other questions? Good? All right.